Alright, so to go along with enthalpy changes, let's talk thermochemical equations. This is very similar to chemical reactions or chemical equations that we've seen before, but we add a heat component to it. So, prior to this point, you've been able to get away with giving me something like this. C2H4 plus 3O2 yields 2 CO2 plus 2 H2O. Alright, you can tell your reactants and your products. You can tell, how many of each thing that you need, like that you need to put in 3 oxygens and you get out 2 carbon dioxides and 2 waters. We call that the whole balancing thing. Alright, a thermochemical reaction is going to maintain these components and add a little more information. So a thermochemical equation would look like this. Alright, so you still have those same reactants, your same products. You still have the balanced equation. Alright, but some new things. You've got states. Alright, these all happen to be gases. You also have your delta H. Alright, what does that stand for? Alright, I'm going to tell you the enthalpy of your reaction. Enthalpy. Alright, and from that you can get even more important information. Like, for example, since this is a negative delta H, a negative enthalpy, would this be endothermic or exothermic? Alright, and then since we know it's exothermic, this is something that gives off energy and heat. Which makes sense, because this is a combustion reaction, which is like burning things. Alright, so thermochemical equations are going to give you some more details. So, the state abbreviations, there's the 3 that you are familiar with, gas, liquid, and solid. Alright, so GL and S. But you will also see the term AQ, which stands for aqueous. What does that word make you think of, aqueous? If it makes you think of like Aquaman and water, that's a good thing. Alright, so aqueous means dissolved in water. Alright, which especially for, say, like an ionic compound, means the ions are separated, which might allow certain reactions to take place that wouldn't happen if it wasn't dissolved in water. Alright, so if you see aqueous, that just means it's dissolved in water. So, thermochemical equations, when you write them correctly, you are going to have your reactants and your products. Those are those chemical symbols with the subscripts. You are going to tell me how many of each you need via balancing. You're going to tell me what state everything is in. And you have to provide the enthalpy per mole. Alright, so kilojoules per mole, joules per mole, something like that. Alright, I noted that it's measured in mole on purpose. That's an important thing just to kind of keep in mind going in the future, is that when you do calculations with this, it is per mole. So, I've got 2 examples down here. This first one, what is missing? What was the mistake this student made when they wrote this one out? What of our components is missing? Alright, that one is missing the states. Not telling me which is gas and which is liquid and things like that. Alright. How about the next one? What is missing here? This one's a little bit trickier, maybe. We really gotta remember how to balance an equation. Alright, so this one is not balanced. You can tell it's not balanced because we put 1 iron in, but somehow we got 2 irons out. Uh-oh. That can't happen. If you remember conservation of mass, Everything that goes into a reaction has to come out. Nothing can be created or destroyed. It has to all be there. So this equation still needs to be balanced. So an example of a problem you might see related to something like this is for the reaction CH4 plus, so methane plus 2 oxygens yields carbon dioxide and 2 waters. What will the change in enthalpy, what will be the change in enthalpy when 3 moles of methane react in excess oxygen? All right, that's where remembering that this delta H is given to us. This is negative 890 kilojoules is given off per mole. All right, that would be your reactants. All right, so this would be how much is given off for 1 mole of CH4. We want to know how much energy would be given off if we burned 3 moles of NH4. I hope this sounds really easy to you, but if 1 mole would create 890 kilojoules, 3 moles is just going to create 3 times that, or 2,670 kilojoules. All right, so you just multiply that by 3. Not horribly difficult, just something you want to, sometimes they don't always write the per mole, so just keep that in mind. Another thing that I want you to be aware of is thermochemical equations don't always have to be written for reactions, like chemical reactions. They can also be written for state changes, right? Because there's a change in enthalpy when, say, water gets boiled. So you can write a thermochemical equation. Here we've got liquid water going to gas water, which absorbs 88 kilojoules per mole. You also can write thermochemical equations for the dissolving of a solid or making an aqueous solution. All right, so here we have ammonium chloride that is being dissolved, all right, broken, added to water, stirred up, and when that happens, it'll split into its separate ions. There should be a plus sign there. And that happens to absorb 14.8 kilojoules per mole. All right, so don't let this throw you off if you see something that doesn't quite look like a reaction. You can do thermochemical equations for state changes and dissolving to anything that involves a change in enthalpy.